Hi, we're going to calculate the concentration and equilibrium given the initial concentration and a Ka value. So this is going to be another acid reaction. You'll recall that we always have three key pieces of information when we're dealing with our equilibrium expressions, okay? We're going to have our K value, and in this case it's specifically Ka, the ionization constant, equilibrium constant for the acid reaction, acid plus water. That's the first piece of information. Second is the initial concentration, and third is the equilibrium concentration. You'll always be given two pieces and you have to find the third. In this case, we're given initial concentration and the equilibrium expression, the ionization constant for the acid reaction. And we have to find E. It wants us to find two things: the equilibrium constants, equilibrium concentrations, and the pH. Okay. So we set up our ice table. I've written my equation initially. So I'm going to start with this hydrofluoric acid. Now, a little note, remember, hydrofluoric acid is considered a weak acid. Is it powerful? Oh, it can do major damage, yes. But it's considered weak because it only partially ionizes. And I'll tell you what, it's a good thing, because even partially ionizing, it is dangerous. This is a common mistake. All of the other halogens, our binary acids, are strong acids: hydrochloric, hydrobromic, hydroiodic. So students easily mix this up and go, oh yeah, it's a binary acid, halogen fluoride with the hydrogen. This is weak, so burn that in your brain, memorize that. HF is a weak acid. So when we drop it in water, it only partially ionizes. A small amount, about 5%, is going to actually react and produce this fluoride ion, and the hydronium is going to come into beautiful equilibrium. Forward rate equals reverse rate. Okay, so we drop the HF into water. Remember, water as a liquid, we don't use it in our equilibrium expression. We only use aqueous and gases, gas phases. We have no fluoride ion, no hydronium at the very beginning. Now the change, so I'm looking at those molar coefficients. For every 1 mole that I lose, I'm going to lose an amount of that HF will react. We are going to produce 1 mole of the F, so that's going to be plus X, and 1 mole of the hydronium, so that's plus X. Love the section on E. All we have to do is add these up. I plus C. We get 0.015 minus X, 0 plus X is X, 0 plus X is X. Okay, now let's write our equilibrium expression. We're going to have the Ka, so our equilibrium constant, also called the ionization constant for the acid reaction, is going to be the fluoride ion raised to the 1 power times the hydronium ion raised to the 1 power divided by the hydrofluoric acid. Now I'm going to plug in everything I have. We've got the Ka, that is 7.2 times 10 to the minus 4 equals X times X will give me X squared divided by 0.015 minus X. Okay, now if I did all of this math, we'd end up doing the quadratic equation, but we have a trick. And if you haven't seen this trick before, go back to my acid-base equilibrium playlist, and I want you to watch the video where it says remove X, ice tables, remove X. Here is your takeaway. If there is a factor of 100 difference, okay, 100, so 2 zeros, between your concentration and your Ka value, your equilibrium constant, you can count this X next to the concentration as negligible. And here's the reason why. Once we solve for X, that number is going to be so small that when you subtract it from this number, it's still just going to be that number. So let's see, do we have a factor of 100 difference? Well, here I'm at the tens place, and here I'm at the thousandths place. So this would be 2 zeros, that's going to be 4 zeros. Yes, barely. I have 2 zeros different, which means I can take this X, and that is going to be negligible. Rule of thumb, for sure, if you're at 10 to the minus 5 or smaller on your equilibrium constant, go ahead and count X next to the concentration as negligible, because we can't get molarities that are going to be smaller than the thousandths place. If it's 10 to the minus 4 or larger, you need to check, are there 2 zeros in between 2 decimal places? in between the number that you have for molarity and the power that you have on that exponent. So this one we barely made it so that we could count that x as negligible. Now a little reminder, you can't count this x as negligible because that x is by itself is not being subtracted from a large concentration or larger, relatively larger concentration. Okay, so x is negligible because there are 2 zeros in between that hundredths place and that thousandths place. Okay, now we just have a little bit of an algebra problem. I am going to multiply both sides by 0.015. Let's do this times 0.015. And then what we'll do is I'm going to take the square root of this entire problem. So if we do the square root like that, we're going to get x equals, and let me tell you, x is going to equal 0.012. 0.012. Okay, great. So now we can go back and just plug everything in. So if we plug this in, I'm going to get 0.015 minus 0.012. What's that going to give us? 0.003. And then here I have 0.012, 0.012. Those are going to be my concentrations. You'll recall all of the concentrations on the ice table, they're all molarity. So by definition, I could just put a big M like this. So M. Now, if I want to know pH, here's the key, is that hydronium ion right there. Our formula for pH is pH equals negative log of the hydronium. Remember, that's the same thing as the hydrogen ion. Chemists use those two terms interchangeably. So let's go ahead and plug that in. pH equals the negative log of, we had 0.012. Okay, and let me put that in my calculator for you. So we will have the negative log of 0.012, and that gives us a pH of 1.92. Ooh. And that makes sense, that makes sense. That's going to be pretty acidic for our hydrofluoric acid. 10 to the minus 4 right here shows us that it's a weak acid, but if you compare all the weak acids, it's going to have some oomph. It's going to ionize more than other weak acids. So that 1.92 doesn't surprise me. Okay, so there you have it. The key is remembering you're looking for 3 pieces of information. Ka equal initial concentration, equilibrium concentration. Somewhere in your problems, you'll always be given 2 pieces of information. You find the third. If you're finding the equilibrium, use that trick if you can, so you don't have to do the quadratic equation. Most of the time, you can count that x is negligible. Solve for x, boom, you've got equilibrium concentrations, and then you just take the hydronium ion to find pH. Pretty slick, pretty smart. Good job, you're doing great work. Have a nice day, thanks.